Hi everyone, how are you? I hope you all are doing very well. This is Conduction live session number 3. We are going to discuss STD heat conduction in one dimension. That is one dimensional STD heat conduction without internal heat generation. A very simple differential equation for such problem. Right. Second order differential equation. We need two boundary conditions to get particular solution. Right. STD heat conduction. One dimensional STD heat conduction without heat generation through plane wall. We'll use STD heat conduction equation in Cartesian coordinate system for plane wall or slab. We actually choose a symmetrical coordinate system that can solve heat conduction problem easily. So that according to bodies, we have a convenient heat conduction equations. Right? For plane wall heat conduction equation in Cartesian coordinate system. Solves problem very easily. For cylinder, we have a cylindrical heat conduction equation in cylindrical coordinate system, and for a spherical body, we have a spherical coordinate system. So we are going to solve heat conduction problem through plane wall, where temperature is not varying with time at any location, and there is no heat generation, and temperature variation in two mutually perpendicular directions are negligible. Temperature is varying in only one direction. It is not varying with time. There is no internal heat generation. The problem is most simplest, and it is one dimensional STD heat conduction without internal heat generation. We are taking plane wall. So this is the differential equation. It is second order differential equation. We integrate this equation 2 times to get its general solution. First time integration yields dt dx is equal to c1. If you differentiate this, you will get this. Differentiate both sides with respect to x. Left hand side becomes dt2 dx2, and the differentiation of constant on right hand side gives 0. So we are getting this. As we know, differentiation and integration both are reverse of each other. After integration, we are getting this. So if we differentiate this, we will get this. Integrating again on both sides. So this will give t, and here on the right hand side c1x plus constant of integration for second time integration. This is your problem. A wall of thickness L having T1 temperature on its left face and T2 temperature on its right face. And this is the thickness of wall. T1 is greater than T2. Right? So here temperature is varying with x, heat x-axis on this side, along this side, and temperature axis in this direction. So at any x, we can find T, because T is the function of x. So this is temperature profile along the thickness of this plane wall. Right? At x, this is T. Right? Move by distance dx. So this is final temperature. This minus this is change in temperature dt. So in dx length, temperature is changing. Temperature is changing with x. Temperature is the function of x. Because here temperature is varying x linearly, right? So this is a straight line variation of temperature along the thickness of this plane wall. This result is providing a straight line temperature profile in the plane wall under STD one-dimensional without internal generation heat conduction. Dear students, in order to get values of arbitrary constant C1 and C2, we need two boundary conditions. At x is equal to 0, temperature is T1, and at x is equal to L, temperature is T2 all the time, because temperature is not changing with time. Temperature is changing only with x, not changing with time. Whatever the value of temperature at x is equal to 0, this will remain same all the time. Whatever the value of temperature at x is equal to L or anywhere in the thickness of the plane wall, with time it is not changing. Right? So this is way to write boundary conditions. Temperature at x is equal to 0 at any time is equal to T1. Temperature at x is equal to L at any time is equal to T2. For these two boundary conditions, at x is equal to 0, temperature is T1. So T1, C1 into 0 plus C2. C2, value of C2 is T1. Now, this solution becomes T1 is equal to C1x and the value of C2 is T1. At x is equal to L, temperature is T2. So from this we can find the value of C1. The resulting solution of one-dimensional STD heat conduction without internal heat generation is this. You can check. Put the value of x is equal to 0, you will get the value of temperature T1. X is equal to 0, temperature is T1. You can see on the left face of the plane wall. At x is equal to 0, temperature is T1. At x is equal to L, temperature is T2. Put the value of x is equal to L, you will get T is equal to T2. On the left face, which is at x is equal to 0, temperature is T1. And at the right face, or at x is equal to L, temperature is T2. So you can get these two boundary conditions. From Fourier's law of heat conduction, conduction heat transfer rate Q dot X. This symbol is showing heat transfer rate through any plane at a distance x from the origin. Through any plane. Q dot X means heat conduction rate through a plane at a distance x, and x is varying, is equal to minus k cross-sectional area of the plane at x is equal to at x, and temperature gradient at x, dt dx at x. Right, differentiate this with respect to x to get the value of dt dx. If you differentiate, you will get minus T1 T2 upon L. Put the value of dt dx here. Dt dx here. Minus plus Ka T1 minus T2 upon L. Ka T1 minus T2 upon L. So dear friends, heat conduction rate across plane at distance x from the origin is constant value. It is not involving x here on the right hand side. Okay. Thermal conductivity of plane wall A, cross sectional area. We are assuming cross sectional area is same at any x. T1 is the temperature of left face and T2 temperature of right face. Because T1 and T2 are not varying in case of STD heat conduction, K and A are also constant, and L is the thickness of the plane wall. So on the right hand side the value is constant, and on the left hand side it is showing heat conduction rate through a plane at distance x. X is variable. X can take any values between 0 and L. The plane at x may be anywhere between 0 to L. X is equal to 0 to x is equal to L. कहीं भी हो सकता है ये प्लेन, ये भी है, ये है, ये है, ये है. The conclusion is that in this case heat conduction rate remains same through any plane between x is equal to 0 to x is equal to L. Right hand side is not involving location of plane. It means heat conduction rate remains same through any cross section between x is equal to 0 to x is equal to L. This is the biggest conclusion. So dear students, we have calculated heat conduction through plane wall in case of one-dimensional STD heat conduction without internal heat generation is equal to T1 minus T2 upon L upon K. This is the result. So this is valid only when cross-sectional area remains same throughout the thickness of the plane wall, thermal conductivity remains same, right? And temperature at any location is not varying with time. So guys, this is same through any cross section. इससे इतना ही होगा, उससे भी उतना ही होगा, इससे भी उतना ही होगा, इससे भी इतना ही होगा. थ्रू आउट क्रॉस सेक्शन हीट कंडक्शन रेट इन किलोवाट सेम रहेंगे. दिस इज द रिजल्ट. सेकेंड मेथड, heat conduction through wall is equal to minus k dt dx. Apply variable separable, bring dx here and minus k dt. At x is equal to 0, here we are integrating with respect to x. So put the limit of x on the left hand side. So lower limit of the x is equal to 0. Here we will put the limit of t is equal to t1. At x is equal to L, t is equal to t2. Under these limits, integration is this result. And finally this. Right? So without getting temperature profile, through this second method, by this second method, we can directly find the heat transfer rate by conduction through plane wall under STD one dimensional without internal heat generation condition. इतना बात याद रखना. This result is valid only when heat transfer is taking place in only one direction. Let's say x. No heat generation and temperature is not varying with time. Thermal resistance concept. Dear students, this point is representing left face of the plane wall and this point is representing right face of the plane wall. At the left face, temperature is T1 and at the right face, temperature is T2. And this is heat transfer due to conduction through the plane wall. And its value is T1 minus T2 upon R. This R is called thermal resistance and its value is L upon Ka. Likewise, electric current flowing under potential difference V1 minus V2 through electrical resistance Re. Likewise, result we are getting in here Q dot is equal to T1 minus T2 upon thermal resistance. Similar. Electrical analogy. It's fine. Convection heat transfer. Consider convection heat transfer from a solid surface of area AS. This is surface of the solid of area AS at temperature Ts to a fluid sufficiently far from the surface where temperature is T infinity. Right? So here we have a fluid. So heat transfer mode will be convective. Conduction plus bulk fluid motion is called heat convection. So heat convection is improvement over conduction due to bulk fluid movement. We can define convective heat transfer. It is enhancement in conduction heat transfer rate due to bulk fluid movement. Convective mode of heat transfer involves moving fluid. Movement is set by naturally or by external means like fan or pump. If movement in the fluid is caused due to buoyancy force due to density difference, this is called natural convection. And if the movement is caused due to external agent like fan, blower, this is called external convective heat transfer. Right. So, dear students, temperature T infinity is the temperature of fluid sufficiently far away from the effect of this surface of solid. So, this is analogous to flow of electric current through electric resistance under potential difference of V1 minus V2. So here temperature potential difference is T1 minus T2, T1 minus Ts minus T infinity. Right? And convective resistance 1 upon HAS. H is convective heat transfer coefficient. AS is surface area of the solid involved in convection mode of heat transfer. Right? So dear students, convective heat transfer rate is equal to convective heat transfer coefficient, surface area of the solid, temperature of the solid minus temperature of the fluid far away from the effect of the solid, and we can arrange like this, right? So convective resistance 1 upon HAS. 1 minute, इसको धुल दूं मैं, कौन है यह है टुन 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 बजा रहा है, कौन टुन टुन है ये, ससुर सुधरेगा नहीं, ये टुन टुन कौन है, न्यू स्टूडेंट है. Radiation heat transfer. The rate of radiation heat transfer between a surface of emissivity epsilon and area S at temperature Ts and the surrounding surface at temperature T surrounding can be expressed as, this is radiative heat transfer rate between a surface of emissivity epsilon, surface area As, surface temperature Ts, and a large enclosure like our environment surrounding. Dear friends, its surface area As, temperature of the surface is Ts, its emissivity epsilon, and we have a large enclosure. Later we will see why we are taking such example, because for this condition, this is the expression for radiative heat transfer, radiative heat exchange between surface and surrounding. For this type of problem especially, this is very large as compared to this. Later we will establish this relationship in the topic of radiation. Why we are taking large enclosure, surrounding is enclosing a surface of area As, a very small surface as compared to surface area of the surrounding, participating in radiative heat exchange. बस अभी इतना ही कर लो. Temperature of the surrounding, T surrounding. So under this condition, radiation heat exchange between surface and surrounding can be written as emissivity of surface, its surface area, surface temperature raised to the power 4 minus surrounding temperature raised to the power 4. We can write this like ts square minus t surrounding square. So this can be written a square minus b square is equal to a plus b into a minus b. Likewise, we are writing here. Again, break this. Ts plus t surrounding minus into ts minus t surrounding. So collect this all together and say it is a radiative heat transfer coefficient. Likewise, convective heat transfer coefficient HCONV, convective heat transfer coefficient. So we have developed a similar heat transfer coefficient involved in radiation heat exchange between a small surface and large enclosure like atmosphere. Small surface kept over a surface and cloud. Temperature of the cloud is this, and surface temperature of the body kept over our surface Ts and its surface area is. So radiation heat exchange between surface and cloud is represented by this expression, and we are getting a simplest expression. So radiative heat transfer coefficient can be written as this. Radiation heat transfer rate Ts minus T surrounding upon 1 upon this value, and this is called radiative resistance. For simplicity, we are arranging equations. Combined convection and radiation heat transfer. Suppose the surface is participating in both convection and radiation heat transfer, right? By both modes of heat transfer, radiation and convection, this surface transferring heat to the surrounding at temperature T surrounding. Surface area A, surface temperature Ts, and by convection and radiation, they are interacting with surrounding, right? So Q total heat transfer rate due to convection plus heat transfer rate due to radiation. Or combined heat transfer rate. So we can write combined heat transfer coefficient, surface area, surface temperature, surrounding temperature. And separately we have defined convection heat transfer rate and radiation heat transfer rate. H convection AS Ts minus T surrounding, H radiation AS Ts minus T surrounding. So friends, here we can write H combined surface area is equal to H combined H convective surface area H. You can take this this common, so this plus this कॉमन कैंसिल हो जाएंगे और रिजल्ट हमें मिलेगा इस तरह से, राइट? So we can calculate combined heat transfer coefficient under this condition. The thermal resistance network for heat transfer through a plane wall subjected to convection on both sides. Now we introduce a problem in which plane wall is subjected to convection heat transfer rate from this side and this side apart from conduction heat transfer rate through the thickness of the plane wall. Dear friends, suppose this is the room wall. This is room, space. And this is surrounding. And we are taking example of summer season. Outside temperature is higher, so T infinity is higher than T infinity 2. Here infinity is showing there is no effect of this surface temperature on the surrounding temperature. We are taking a point far away from the effect of this side. So T infinity 1 is actual temperature of the surrounding, which is away from the effect of this face temperature. Suppose this is the wall of this studio, right? And we are taking a point 10 meters away from this wall. So definitely in summer season, this temperature is higher than this temperature, right? So infinity is actually indicating that we are taking a position and measuring the temperature which is actually away from the effect of this wall. So here temperature is decreasing. As we move towards this phase, temperature is decreasing. And we know heat transfer takes place in the direction of decreasing temperature. So this is the direction of convective 1 heat transfer rate. So from T infinity 1 to T1, we have a convective 1 resistance, and its value here, H1 is heat transfer coefficient on this side, 1 upon H1, and surface area. Surface area is A. So convective resistance on this side is equal to 1 upon H1A. Conductive resistance, and now it is being conducted through the thickness of the plane wall from T1 to T2. So between T1 and T2, this is conductive resistance of the wall. L upon K. L is the thickness, K conductivity of the material of the wall, and A cross-sectional area. And from this face to this side surrounding, again we have convective resistance between T2 to T infinity 2. Convective 2 resistance. Its value 1 upon H2A. Right. So from T infinity 2, T infinity 1 to T infinity 2, add these all resistances to get the total thermal resistance between these two surroundings. इन दोनों सराउंडिंग्स के बीच में टोटल थर्मल रेसिस्टेंस कितना है, इन सब को ऐड कर दो. आफ्टर एडिंग 1 upon H1A plus L upon K plus 1 upon H2A. This is the total resistance between this surrounding and this surrounding. Important point, dear friends. Most beautiful conclusion in the case of one-dimensional STD, heat conduction without internal heat generation, where plane wall involves convection heat transfer modes on both sides, through plane wall conduction and on both sides convection. This Q dot can be written like this: Q dot T1 minus T infinity 1 upon R convective 1. We can also write T1 minus T2 upon same Q dot is flowing through all thermal resistances. T1 minus T2 upon R wall. R wall L upon KA. T2 minus T infinity 2 R convective 2. This is R wall. And dear friends, add these all resistances and write directly T infinity 1 minus T infinity 2 and total resistance between these two temperature potentials. So R convective 1 plus R wall plus R convective 2. All are same. All are same. यह इंपॉर्टेंट पॉइंट था. कभी कभी क्या रहेगा, आपको जो है पूछ देगा जो है ना, T infinity 1, T infinity 2 both are given, right? We can easily calculate this and this. Then problem can ask what is the value of the left face. T1 is desirable. So dear students, equate T1 minus T infinity 1 minus T1, T infinity 1 minus T1 and this total resistance expression for the same heat transfer rate, and then we can easily find the unknown value. बात समझ में आया? कभी कभी T infinity 1, T infinity दिया रहेगा और वो सारे इंफॉर्मेशन दिए रहेंगे जिसमें convective 1, convective 2 and R wall. We can easily calculate. Then problem can ask find the value of T1. That is the temperature at the left face, or temperature at the right face, or temperature at a distance x by 2 from the left face. कुछ भी पूछा जा सकता है. ठीक है, इसलिए कांस्टेंट बोला गया है. ये वन डायमेंशनल एसटीडी हीट कंडक्शन विदाउट इंटरनल हीट जनरेशन में ही पॉसिबल है. ओवरऑल हीट ट्रांसफर कोएफिशिएंट. नाउ वी ब्रिंग अ वेरी इंपॉर्टेंट term, overall heat transfer coefficient. This is usually used in heat exchanger. This is most important parameter in heat exchanger. Overall heat transfer coefficient. Overall heat transfer coefficient. In the previous problem, we can write heat transfer rate across left face, across right face, from surrounding 1 to left face, from surface 2 to surface right surface to surrounding 2, and across any plane at a distance from left face. किसी भी प्लेन के थ्रू रेट ऑफ हीट ट्रांसफर आप ऐसे लिख सकते हो यू ए, राइट, टी इन्फिनिटी 1 माइनस टी इन्फिनिटी, right, T infinity 1 minus, and already we have developed heat transfer rate in the same case involving total resistance R total. T infinity 1 minus T infinity 2 upon 1 upon UA. So dear friends, 1 upon UA is equal to R total. This is the way to calculate overall heat transfer coefficient. In the same problem, we can easily find the value of overall heat transfer coefficient U by equating 1 upon UA to R total, and R total is R convective 1 plus R wall plus R convective 2. R convective 1 upon H1A, R wall L upon K, R convective 2 1 upon H2A. So we can find the value of U, overall heat transfer coefficient, right? Here, in case of plane wall, area of all planes between x is equal to 0 to x is equal to L, or throughout the thickness of the plane wall is same, right? But guys, in case of thick cylinder, here hot fluid is flowing, and this is a pipe. This is the thickness of the pipe, and this is external pipe, right? This is external pipe, and it is insulated from outside. So in this annulus region, cold fluid is flowing, and through the inner pipe, hot fluid is flowing. So this is the direction of heat transfer from hot fluid to cold fluid. गबड़ा हो गया, या इसमें फ्लो हो रहा है कोल्ड. दिस इज थिकनेस ऑफ pipe enclosing inner pipe, right? So hot fluid is flowing through inner pipe, and cold fluid is flowing through this annulus space. So this is the direction of heat transfer, right? So in the direction of heat transfer, you can easily visualize area of flow is increasing. Area of flow is increasing. But in case of plane wall, this is not happening. This is your plane wall. So in the direction of heat conduction or heat transfer, all planes have same heat transfer area. Outer A, this side A and this side also A. But this is actually not happening in the case of pipe flow. So guys, later we'll see how to find overall heat transfer coefficient U in the case of heat transfer involving cylindrical pipe, where in that case we use particular area, and corresponding to that area we define overall heat transfer coefficient, like overall heat transfer coefficient based on inner surface area, overall heat transfer coefficient based on outer surface area. So in that case, guys, UIAI is equal to R total, 1 upon R total, or 1 upon UIAI is equal to 1 R total, 1 upon UOAO R total. देखेंगे हम बाद में, समझ में आ जाएगा. ओवरऑल हीट ट्रांसफर कोएफिशिएंट बेस्ड ऑन इनर सरफेस एरिया, ओवरऑल हीट ट्रांसफर कोएफिशिएंट बेस्ड ऑन आउटर सरफेस एरिया. Clear? But in case of plane wall, inner wall, outer wall, both have same area. So here only one overall heat transfer coefficient can be defined. But in case of pipe, dear friends, here we have air and here hot fluid. So this is the direction of हीट ट्रांसफर. यही तो था. इधर हमारा एक इधर जो ना एटमॉस्फेरिक एयर था इन केस ऑफ प्लेन बॉल. दिस साइड वी हैव एटमॉस्फेरिक एयर एंड दिस साइड रूम स्पेस. Similar situation, hot fluid. This is a cylindrical surface, right? So here we have hot fluid and here we have a cold surrounding. So this is the direction of heat transfer, or this may be the direction of heat transfer in case of higher temperature of air than fluid inside this pipe. So friends, Here heat transfer area is varying in the direction of heat transfer. We have two known heat transfer area, inner surface area of the pipe and outer surface area of the pipe. So count total thermal resistance from inner space to outer space. This is R total. And this can be equated to 1 upon UIAI. So this UI is called, and AI is this 2 pi Ri and length of the cylinder. This is the total surface area of the heat transfer in case of cylinder. And we can also define AO is equal to R total. And this is called, and here AO is outer surface area, 2 pi ROL. And this. So we'll get a different value of UI and UO in case of cylinder and a sphere. So in heat exchanger, we use pipe. A pipe in which hot fluid is flowing, a pipe in which cold fluid is flowing, and we are allowing these two fluids to transfer heat. Right? So in that case, overall heat transfer coefficient based on area, inner area, outer area, have different values. But in case of plain wall, this is not different, सेम रहेंगे. ठीक है ना, समझ में आ गया ना, क्योंकि हर जगह एरिया वही है. देखेंगे, आएगा बहुत बार, प्रॉब्लम भी आए हुए हमारे गेट में बहुत सारे वैसे. हीट एक्सचेंजर में भी देखेंगे. विल सी दिस ऑल थिंग्स इनसाइड heat exchanger. Now introduce concept of thermal contact resistance. Thermal contact resistance. Dear friend, this is layer 1 and this is layer 2. They are two separate layers. Now we bring these two layers in contact. This is the contact. And guys, this is ideal or perfect thermal contact between these two layers. And this is visualized here. Here we have a perfect contact at interface. If surfaces of these two layers are perfectly smooth, in that case they will produce a perfect contact point to point. Each and every point of this side and this side are in perfect thermal contact. In reality, even flat surfaces that appear smooth to the eye turn out to be rather rough when examined under a microscope with various peaks and valleys. आंख को ये भले स्मूथ लगे, बट वेरियस पिक्स एंड वाइलीज दोनों सरफेस पर होंगे. अब दोनों को जब प्रेस करेंगे, इफ दे आर प्रेस्ड अगेंस्ट ईच अदर, पिक्स दे कम इन परफेक्ट कांटेक्ट, बट वाइली both side वाइलीज form void or gap filled with air. Introduce additional resistance. That resistance is called contact resistance, and resistance causes a reduction in temperature. So we'll get at the same location, but in this layer T1 temperature at the same location. On this layer we have T2 temperature, and this is the drop in temperature due to contact resistance. Due to contact resistance, this is the drop. If layers are in perfect contact, there is no drop in temperature. Right? But here, at suppose this is x is equal to xi. representing interface location. Interface. So at interface, temperature corresponding to layer 1 at x is equal to x1 is equal to T1. At the same location, temperature corresponding to layer 2 at the same location, x is equal to x1 is equal to T2. This is happening due to drop in. This is happening due to thermal contact resistance. Contact resistance. Corresponding points on both layers are not in perfect thermal contact. In reality, peak are in thermal contact, and numerous valleys on both layers forms void filled with air, and thermal conductivity of the air is less than thermal conductivity of solid contact. परफेक्ट कॉन्टेक्ट होता तो कैसा होता? सॉलिड पॉइंट्स होते हैं, एयर नहीं फील्ड होता, लेकिन यहां पर क्या हो गए, ये देखो वायर बन गए, इसमें एयर आ गए, तो वही मेटालिक कॉन्टेक्ट होता, एयर नहीं होता, रेसिस्टेंस नहीं होता, लेकिन यहां पर रेसिस्टेंस आ जाएगी उस एयर की वजह से, बिकॉज एयर की थर्मल कंडक्टिविटी कॉन्टेक्ट नहीं होने के कारण, अगर होता तो मेटल कॉन्टेक्ट होती, उससे कम है, तो इट ब्रिंग्स contact resistance that causes drop in temperature. Thus an interface offers some resistance to heat transfer, and this resistance for a unit interface area is called the thermal contact resistance. RC is 1 upon HC into 1. That is 1 upon HC. 1 upon HC. It's fine. 1 upon HC. Heat transfer through the interface is the sum of heat transfer through the solid contact spots, solid to solid conduction, and the gaps, conduction and or radiation across the gap. गैप में क्या हो गया? स्टिल एयर है, स्टिल not moving air. Bulk fluid movement is not happening in the air filled in micro gap. So conduction or radiation through the gap filled with air. अगर वही एक मेटल कांटेक्ट होता, सॉलिड कांटेक्ट होता, तो हीट ट्रांसफर सॉलिड से जाता, उसकी कंडक्टिविटी हायर है एज कंपेयर टू गैस. सॉलिड की कंडक्टिविटी ज्यादा था ना, मेटल हो या नॉन मेटल, गैस से ज्यादा है, बीच में इंटरमीडिएट में लिक्विड है, गैस की कंडक्टिविटी बहुत कम होती है. राइट, दो तरीके से होगा, मतलब कि हीट ट्रांसफर सॉलिड पॉइंट कांटेक्ट के थ्रू होंगे एंड गैप के थ्रू होगा. गैप में एयर है, यही काम कर दे रहा है रेसिस्टेंस का. तो क्यू डॉट थ्रू कांटेक्ट पॉइंट्स एंड क्यू डॉट थ्रू गैप. राइट, HA delta T interface, we can write like this: HCA delta T interface, delta T interface upon 1 upon HAC. This is Q dot at the interface, और 1 upon AC को क्या बोलते हैं हम लोग? कॉन्टैक्ट रेसिस्टेंस. 1 upon HC. तो डेल्टा T interface upon Q dot upon A. This is contact resistance. Right? ऐसे जो हीट ट्रांसफर कोएफिशिएंट एट द कॉन्टेक्ट, जो गैप है ना, उस गैप में जो एयर है ना, ठीक है, और कॉन्टेक्ट पॉइंट से जो हीट ट्रांसफर हो रही है उसी के करस्पॉन्डिंग, उसी के इक्विवेलेंट में इसको डिफाइन किया गया है। कॉन्टेक्ट पॉइंट का ही है, मतलब इक्विवेलेंट हीट ट्रांसफर कोएफिशिएंट है एट कॉन्टेक्ट पॉइंट। कॉन्टेक्ट पॉइंट्स में कितने प्रोपोर्शन में सॉलिड सॉलिड का कॉन्टेक्ट है और कितना एरिया में जो ना वॉइड है, उस पर ये डिपेंड करेगा। वास्तव में टोटल एरिया ए ऑफ इंटरफेस is taken by solid solid contacts and गैप। टोटल एरिया में गैप और कॉन्टेक्ट भी है, तो उसके प्रोपोर्शन पर ये इसकी वैल्यू डिपेंड करेगा। एससी कॉन्टेक्ट पॉइंट के करस्पॉन्डिंग हीट ट्रांसफर कोएफिशिएंट है, इंटरफेस के करस्पॉन्डिंग हीट ट्रांसफर कोएफिशिएंट है, राइट। सो इंटरफेस टेम्परेचर ड्रॉप अपॉन heat transfer rate upon interface area, this is thermal contact resistance। यूनिट जो है ना एससी का उल्टा हो जाएगा, हीट ट्रांसफर कोएफिशिएंट वाट पर मीटर स्क्वायर पर केल्विन, उसका उल्टा कर दो, मीटर स्क्वायर केल्विन पर वाट। जनरलाइज थर्मल रेसिस्टेंस नेटवर्क, डियर फ्रेंड्स, two slabs are in parallel, right? Insulation, this is 1 and this is 2, this face is at temperature T1, this face area is A1, this face area is A2, this face is temperature T2 and this is also at temperature T2. So total heat transfer rate from this to this can be written as total through this plus, clear, खत्म, Q dot 1 you can easily calculate, टोटल ऐसे हो जाएगा ना। तो ये देख लो, इसका जो है ना एनालॉगस, मतलब थर्मल रेसिस्टेंस नेटवर्क क्या हो जाएगा, देख लो, both faces are at the same temperature T1 and right faces are also at temperature T2, both right faces, so though both are conducting heat through same temperature potential difference, same temperature difference, इसीलिए दोनों के लिए सेम रखा गया, सेम this is experiencing same temperature difference T1 minus T2 and this is also experiencing same temperature difference T1 minus T2। दोनों की जो ना लेंथ, हमारा थिकनेस जो ना L है, तो इधर से Q1 गया, इधर से Q2 आया, यहाँ से फिर से ज्वाइन कर गया, तो टोटल हीट ट्रांसफर रेट फ्रॉम दिस साइड टू दिस साइड कैन बी रिटन लाइक दिस, R1 L अपॉन K1 A1, R2 L, both have same thickness, L upon K2 A2, बस। So dear students, it's a equivalent thermal resistance can be obtained very easily, like equivalent electric resistance of two resistances in parallel connection, are equivalent, या R टोटल भी बोल सकते हो, सेम हीट ट्रांसफर रेट होना चाहिए। वहां से क्या लिखोगे, T1 माइनस T2 अपॉन R1 प्लस T1 माइनस T2 अपॉन R2। सेम आया ना, 1 अपॉन R1 प्लस 1 अपॉन R। जब पैरेलल में कनेक्टेड रहते हैं तो क्या लिखते हो, R टोटल इज इक्वल टू R1 R2 अपॉन R1 प्लस R2, like equivalent resistance of two resistances connected in parallel connection. If they are connected parallelly, so same result we are getting in the heat transfer case also. इलेक्ट्रिक करंट निकालते समय जो हम लोग कॉन्सेप्ट लगाते थे, हीट ट्रांसफर रेट में भी वही रिजल्ट आ रहा है। तो फॉर दिस टोटल रेसिस्टेंस बिटवीन दिस एंड दिस इज R1 R2 अपॉन R1 प्लस R2। पैरेलल दोनों के सीरीज में ये है, राइट। तो दिस फेस एंड दिस फेस, दिस बोथ आर एट द सेम टेम्परेचर, T1 this T1 this T2, T1 T2, एंड ये वाला जो है ना आपका T3 पर है। तो दिस एंड दिस आर इन सीरीज पैरेलल कनेक्शन एंड R3 इज इन सीरीज। और यहाँ पर H T इन्फिनिटी दिया हुआ, तो कन्वेक्टिव रेसिस्टेंस भी यहाँ पर T इन्फिनिटी के बीच में आ जाएगा, इधर T इन्फिनिटी, यहाँ से सरफेस एंड इसके बीच में R कन्वेक्टिव। तो वेरी सिंपल, इन दोनों को जो है ना कैसे करोगे, टोटल रेसिस्टेंस कितना हो जाएगा, R टोटल, वी कैन इजीली कैलकुलेट R टोटल R1 R2 अपॉन R1 प्लस R2 प्लस R3 प्लस R कन्वेक्टिव, R1 वी नो वेरी इजीली, L1 अपॉन K1 A1 R2, L2 अपॉन K2 A2 R3, L3 अपॉन K3 A3 R convective 1 upon H A3. The entire area A3 is involved in convection mode of heat transfer with this surrounding. HTS, H heat transfer coefficient for the convective heat transfer between this and this. Here we have a surrounding H, and TS is the temperature of the surrounding which is far away from the surface area A3. Heat conduction in cylinder. Dear friends, one dimensional STD heat conduction without internal heat generation through cylinder. From generalized heat conduction equation, we can write this equation very easily. 1 upon R R, 1 upon R R dt dr, its integration, its differentiation with respect to R. I एंड जेड वाला को छोड़ दो, जनरेशन को हटा दो, एंड dt को हटा दो राइट साइड में, तो बच जाएगा ये केवल रेडियल डायरेक्शन में हीट कंडक्शन हो रही है. दिस इज वन डायमेंशनल एसटीडी हीट कंडक्शन विदाउट इंटरनल जनरेशन थ्रू सिलेंडर. तो डायरेक्शन क्या हीट ट्रांसफर का? रेडियल डायरेक्शन में, रेडियली ऐसे सिलेंडर है तो सेंटर से अब ऐसे हीट ट्रांसफर हो रही है रेडियली, इंटीग्रेटिंग both sides 2 times. This is general solution of this one dimensional STD heat conduction without internal heat generation through cylinder. Boundary condition. Dear friends, we have a specified boundary condition. Suppose in this problem given that inner surface temperature is T1, outer surface temperature is T2. So at R is equal to R1 temperature is T1, at R is equal to R2 temperature is T2. Boundary condition related with dimensions are called conditions related with dimensions are called boundary condition. So at R is equal to R is equal to R1 is the dimension. At R is equal to R1 temperature is T1, at R is equal to R2 temperature is T2. Put these two boundary condition in order to get two arbitrary constant values. putting the value of arbitrary constant, you will get temperature variation with R. Temperature is varying with radius. Temperature varies radially. If heat transfer takes place from inner to outer side, it means temperature of inner space is higher than temperature of the surrounding. So radially. It's fine. So dear friends, after putting these two boundary conditions, we have obtained temperature variation with R. No need to remember this. Temperature variation with R. Likewise, temperature variation with X in case of one dimension STD heat conduction without internal heat generation through plane wall. In case of plane wall, we have used equation in Cartesian coordinate system because or Cartesian for plane wall Cartesian solves problem easily. So here in case of cylinder, one dimensional STD heat conduction without internal heat generation in a cylindrical coordinate system solves problem easily. So that guys, we have written one dimensional conduction or the heat conduction equation in three different coordinate system. That's why we have one more question in gate 21 or 22 from equation of heat conduction. इसीलिए पूछा गया था, इतना इंपॉर्टेंट था ये. फिर वही फंडामेंटल है, उसी को उड़ा दोगे आप, ठीक है, उसको मेमोराइज नहीं करेंगे बट वो तो जानेंगे ना है क्या वो. दिस इज a standard way in your BTech to study your syllabus. ऐसे डायरेक्ट फार्मूला लिख लिया, चल दिए. डिफरेंशियल कहां से आया, कैसे आया, डिफरेंशियल क्वेश्चन को भूल जाएंगे. वो भी आपके पास जो ना मैथमेटिक्स, इंजीनियरिंग मैथमेटिक्स एक सब्जेक्ट है ना. 3 सेमेस्टर एटलीस्ट पढ़ाए गए होंगे आप लोगों को. उसी का तो एप्लीकेशन था. उसको छोड़ने का मतलब यू आर नॉट गोइंग टू सॉल्व गुड प्रॉब्लम्स ऑफ हीट ट्रांसफर. उसके अच्छे प्रॉब्लम इक्वेशन से बेस्ड होते हैं, अच्छे स्टूडेंट सॉल्व करते हैं और सब्जेक्ट की भी जानकारी हमारी बहुत अच्छी हो जाती है. कहाँ कुछ किया मैंने. आफ्टर पुटिंग दिस टू बाउंड्री कंडीशंस we have obtained variation of temperature with R. With R is varying like X is varying. R is equal to R1 is a fixed position. R is equal to R2 is fixed position, but simply R. It may take any value between from R1 to R2. From R1 to R2, it can take any value because from R1 to R2 conduction through the material of cylinder is taking place. R1 is the radius of inner surface of the cylinder. R2 is the radius of outer surface of the cylinder. Through the thickness of the cylinder from R2 minus R1, conduction mode of heat transfer is taking place. We are discussing conduction here. This relationship is valid only for R is equal to R1 to R is equal to R2. उसके पहले उसके बाद तो बात ही नहीं किया मैंने. Thickness of cylinder starts from R is equal to R1 to R2. Total thickness R2 minus R1. In this thickness, material of cylinder is actually present, and through this material, conduction mode of heat transfer is taking place. Dear friends, now we are going to find heat transfer rate. After getting variation of temperature with R, variation of temperature with its independent variable R, now we are perfect candidate to calculate the value of heat transfer rate, because heat transfer rate minus Ka, A cross sectional area. 2 pi r into length of the cylinder. R1 r. We are taking intermediate cylindrical surface of radius r. Length is L and this is R2. So 2 pi r into L. This is the total surface area of the heat transfer. 2 pi r into L. Temperature gradient. Temperature is varying with R. So temperature gradient. Space variable इसका क्या है? R है. Right. So guys, find dt dr at any location at r is equal to r1. Right. जब सॉल्व करोगे इसको, कुछ नहीं करना है, इसको डिफरेंशिएट करना है, r इक्वल टू r1 पुट करेंगे तो आपको जो रिजल्ट मिलेगा वो रिजल्ट ये है. और यहां से जो है ना इसी फॉर्मेट में आया T1 माइनस T2 thermal resistance of cylinder and this is equal to this. और सेकेंड मेथड डायरेक्ट जो है ना फूरियर लॉ ऑफ हीट कंडक्शन को डिफरेंशिएट करके आप इंटीग्रेट करके ला सकते हो. राइट. तो एस्टेब्लिशमेंट क्या हुआ वो करके लाया गया डायरेक्ट. क्या मिला आपको डियर स्टूडेंट्स? सपोज दिस इज द टेम्परेचर T1. right. From this to this we have convective mode of heat transfer because अगर इसमें लिक्विड भरा है, फ्लूइड भरा है, convective one from center to inner surface. Inner surface temperature is T1 and between inner surface and outer surface temperature is decreasing due to conductive resistance of the cylinder, R cylinder, and this is T2. And from T2 to outside surface T infinity, simply T infinity, we have R convective 2. इस तरह से टोटल रेसिस्टेंस क्या हो जाएगा? R टोटल R convective 1 plus R cylinder plus R convective 2 and R cylinder is R2 upon R1, बड़ा अपन छोटा ln R2 upon R. नहीं घबरा रहा है. R2 upon R2 सॉरी ln R2 upon R1 2 pi KL upon 2 pi KL. ln R2 upon R1 2 pi KL. Very simple ना. ln R2 upon R1 2 pi KL. K is the thermal conductivity of cylinder material. L length of the cylinder. बात समझ में आया? अब आइए मल्टी लेयर्ड सिलेंडर पूरा करना है तो कर लो, जगह कम था मेरे पास, करना है कर लो. सिलेंडर ही सिलेंडर है, एक को जो ना गिरता हुआ दूसरा ऐसे ऐसे करके. फ्रेंड्स, from this point to this point we are going to write total resistance. Here temperature is T infinity 1. T infinity 1 to this is surface 1. Its temperature T1. We have a convective resistance 1, R convective 1, and suppose here H1 and so we can write 1 upon H1 and this area A1. Now we have conductive resistance of cylinder R2 R1 ln R2 R1 upon 2 pi K1 into L. Suppose all cylinders have same length L. from this to this, again we have conductive resistance R3 upon R2 ln R3 upon R2 2 pi k, all have same length. 3 to 4, surface 4, its radius is R4 ln R4 upon R3 upon 2 pi kl, and from this to this we have a convective resistance 2, 1 upon H2, 1 upon H2, and this surface area is involved actually, and this is A4, 2 pi R4 into L, this is A4. बात समझ में? A1 2 pi R1 into L, A1 done. So total resistance we can easily calculate all these resistances and get the value of total resistance. बात समझ में आया? इसमें भी सेम ही ट्रांसफर रेट होती है, Q डॉट R, यहां से निकाल लो और इसको आप इसे भी, इन दोनों को रेसिस्टेंस को ऐड करके T3 माइनस, ऐसे भी कर सकते हो, देखो कैसे कैसे इसके साथ क्या क्या कर सकते हो, T1 माइनस T इन्फिनिटी 1 माइनस T1 अपॉन R कन्वेक्टिव 1, ये कुछ भी लिख सकते हो आप, पकड़ लो इन दोनों को, T4 माइनस T2 अपॉन दिस प्लस दिस R सिलेंडर 2 प्लस R सिलेंडर 3, तुमको जो मन करता है इस यहां से लेकर यहां तक पकड़ लो, T इन्फिनिटी 1 माइनस T इन्फिनिटी 2 डिवाइडेड बाई टोटल रेसिस्टेंस अवॉइड कर दो, यानी जो टेम्परेचर रखोगे उसके बीच का टेम्परेचर रेसिस्टेंस निकल डिनोमिनेटर में रखना पड़ेगा, वही सारी चीज यहाँ पर बोला गया है, कंप्लीटेड। तो आज ये वाला सेशन आपका काफी इंटरेस्टिंग था, ढेर सारे प्रॉब्लम को सॉल्व करने के लिए, समझ में आया? राइट, तो फ्रॉम माय साइड दिस इज द एंड ऑफ थर्ड सेशन। अब आपको कहीं जो है ना कंफ्यूजन है तो हमसे पूछ लीजिए, कहाँ दिक्कत आई है, इस सारे डिस्कशन मुझे नहीं है, आप जान लो, तो फिर आपके प्रॉब्लम को मैं रहने नहीं दूंगा, सॉल्व कर दूंगा। बताइए कहाँ प्रॉब्लम है।